Hi students, welcome to Power Electronics Laboratory. In this video, we'll discuss about single phase fully controlled rectifier with R and RL load, right? So we've already studied this in the theory part. So we'll discuss here with respect to R load and RL load, where R is nothing but resistive load. RL means resistance and inductance both will be in series. Now, the aim of the experiment is to study the output waveform of a fully controlled rectifier with R and RL load and its effect of freewheeling diode. To plot output voltage versus firing angle alpha for R and RL load operation. So this is our aim. Now freewheeling diode will come into the picture only in RL load and freewheeling diode will be absent in R load. So this is the apparatus required. We need a single phase fully controlled bridge converter power circuit, and then we need a single phase firing circuit, single phase isolation transformer, rheostat, inductance and CRO. So these are the apparatus which we require for this experiment. Now this is the circuit diagram which we'll be using for this experiment. So this is the auto transformer where we can vary the voltage from 0 to 230 volts. And this is a single phase isolation transformer which is used to isolate the supply and the converter, and this part and this whole thing is a part of the kit where we need to connect using connecting wires, right? And this is the load. So here it is in general, it is mentioned as R load as well as L load, right? So if we connect only resistance here, that is, if we connect only the resistor here, if we connect only the resistor here, that is resistance R, this becomes R load, and if I put an inductance in series, that will become RL load. And again with the RL load, if I connect one diode here, that becomes RL load with freewheeling diode. So the whole part remains the same, only in this part will have some changes, right? That I'll explain when we are doing the connections. So we'll move on to the next slide. So this is the tabular column, serial number, firing angle, alpha, V0 practical. V0 practical will be observed from CRO, right? And V0 theoretical will be calculated using the formula. Now these are the waveforms which will be seen in the CRO. Now V in, as you all know, the input voltage will always be sinusoidal. So we'll apply a sinusoidal to the sinusoidal supply as the input AC. And this is a firing angle 0 to 180 degrees. It can be fired anywhere from 0 to 180 degrees. So if we fire at this point, if we fire the supply, if we fire the switches at this point, then until that point, that is alpha, the voltage will be 0, output voltage, and from that point, whatever is the input, that same input will be available here. So from here you can see that if alpha was 0, we would have got a full supply voltage, and if alpha is 180 degrees, then the output voltage will be 0. You have to note that here. So whenever the switch is off, whenever the switches are off, that voltage will be available across the switches. So from 0 to alpha, whatever voltage here it was 0, that voltage will be dropped across SCR, right? This is the basic things which you should know, right? So this is for RL load, right? So now here for R load, we'll have a continuous. Now if this was alpha, this will be the waveform, right? Until this, it will be 0, and only here we'll have the voltage waveforms, and here it will be 0, right? And from inspection itself, you can know that here alpha is more than 90 degrees. For L load, RL load, what happens is you'll have the same thing here from alpha to pi, and here you'll have a negative part because of discharge of inductance. Because of discharge of inductance, you'll have negative part. So to eliminate this part, so what do you mean by rectifier? Rectifier is a circuit which converts AC to DC. So now since we have negative part here, we cannot tell it as pure DC. So to eliminate this one, we need to connect a freewheeling diode. So when we connect a freewheeling diode, this peak will be reduced. This peak will be reduced. So this peak will be reduced. So see, you can compare from here to here. The peak will be almost zero. It will be similar to R load. So even though if you have RL load, when you connect a freewheeling diode, RL load will be, the output will be similar to R load, right? That is the advantage of freewheeling diode. So here you can see this is RL load and this is RL load with freewheeling diode. I hope you have understood the difference between RL load without freewheeling diode and RL load with freewheeling diode, right? So now let us do the connections. So now first, as I told you, this basic diagram, this diagram will remain the same, right? Only thing is here when I connect a R load, when I connect R load here, it will become fully controlled rectifier with R load. If I connect RL load, it will become fully controlled rectifier with RL load. If I connect RL and one diode, it will become fully controlled rectifier with RL load and freewheeling diode, right? So that you have to understand. Now here these are the things what we require. One is auto transformer, isolation transformer. This is auto transformer. This is isolation transformer. This is single phase firing circuit. This is CRO to see the output. And this is rheostat, that is R load. And this is inductance, that is L load. And this is multimeter to see the practical voltage, right? So now we'll see how to do the connections here. Now first thing what we'll do is we'll connect the auto transformer to isolation transformer. So here you can see now this auto transformer is connected. This auto transformer is connected to single phase supply. So positive of auto transformer and negative of auto transformer, right, is connected to an isolation transformer. So what we'll do is we'll connect this wire to 0 and one more wire will connect it to 240 volts. So what we have done here, we have connected auto transformer to isolation transformer. Now the supply will be available here. This auto transformer and this isolation transformer, you have to remember that it will be used only to isolate the supply and the load side, right? It will have different ground. For that purpose we'll be using this isolation transformer, or else we'll have some problems with respect to firing. That is why this isolation transformer is required. Now we have to connect this to the kit. Now here we have finished this connection. Now isolation transformer, you can just see this isolation transformer now is connected to secondary of isolation transformer is connected to the MCB. Now here this 0 volts, I'll connect it here, and 240 volts will connect it here, right? Now the supply is given to the kit here. Now from the MCB, this should be in off position always. When we on the supply will be available here. So whatever supply is here, that supply will be available here, right? Now from here, before doing this connections here, we'll finish off this connections. That is this connection here. You can see 4 resistors connected in this way. 4 this thing thyristors are connected in this way, CRs. Now I will take this T1, T2, T2 dash, T1 dash and T2 dash, right? T1, T2, T1 dash, T2 dash. Now how are these connected? Now you can see that this anode is connected to T1 cathode. So we need to connect a wire from here to here, and again here there is one more connection from anode to cathode. So from this point I'll connect one more wire here, right? And these two are connected, and here these two are connected. Done. So we have done this now, we have done this connection now, right? And now how to connect this MCB? This MCB should be connected to either anode of T2 dash or cathode of T1 dash. So we'll connect it to cathode of T1 dash, T1. So this will be connected to the MCB here, right? Now the other point of the MCB, that is negative, is connected to cathode of T2. That is cathode of T2 is here. So this wire will be connected here. This wire will be connected here. So we have finished giving the supply to the bridge, right? So now this connections will always remain the same for any type of the load, right? So now we'll see how to connect the resistive load here. So this is the freewheeling diode, you can see here DM. This is the freewheeling diode. Now how is the load connected for our load? So for our load, the load will be connected in this way. That is our load. So I have to connect the rheostat here. So what I'll do is I'll take one wire and connect it from here to this rheostat, and I'll take one more wire from here and I'll connect it to this point of rheostat. Now the circuit is done. Now how to take the readings? We have to set this auto transformer to some 80 volts, right? You can set it to some 80 volts, and then full 80 volts will be available here after isolation. So 80 volts is given here. When you switch on the supply is available here. So that supply is given to the bridge, and the operation of this bridge will operate, and now it will go through the R load, right? Now how to connect the CRO? Now here you can use either channel A or channel B, right? So you know that we'll have a wire, we'll have a probe in which you'll have red and black wires. So that probe will be connected across this rheostat, will be connected across this rheostat, right? And now for measurement of practical voltage, we have to connect one more wire. That is, now I'll show in different color. So what I'll do is I'll connect a multimeter across the load. I'll connect the multimeter across the load, right? So now how to operate this? You have to set this to 80 volts. You have to switch on the MCB, right? And now one more thing is we have not given the firing pulses yet. Now here you can see that we have four switches here: T1, T2, T1 dash, T2 dash, right? So here also it will be written, that is T1, T1 dash, T2 and T2 dash. So the same kind of connection should be given here, right? So now T1. So you have to take a wire and connect from this green, T1 green, to this T1 green, right? Next T2 or T1 dash, right? Where is T1 dash? T1 dash is here. So this green will be connected here, right? Again T2, T2 will be here. So here T2, so this T2 is connected here, and the last one T2 dash. So T2 dash will be connected here. T2 dash will be connected here, right? Now how to connect the black wires? Black wires should be connected in this way. That is, so I've taken a black wire. Now this T1 will be connected to this wire, right? Again T2, T1 dash, T1 dash will be connected here, right? Again T2, T2 will be connected here. The last one T2 dash, T2 dash will be connected here, right? So this is how you have to do the connections. I know that these are complex connections which you cannot make out from the screen what you are seeing now. Simple way, here you have T1, T2, T1 dash, T2 dash, right? So the same switches you have to give the connections here. I hope you have understood this. Now coming to the operation part, first you have to switch, first you have to give 80 volts here. Once you give 80 volts, you have to switch on the MCB, and then this is your firing pulses. This is your firing pulses. So first you have to keep that at 0. You can start it from 0. Alpha is equal to 0. Then you have to observe the waveforms here, that is in the CRO, and then you have to see what is the voltage here and make sure that this multimeter is kept in DC mode. This multimeter is kept in DC mode, and then you have to measure the you have to measure the voltage and note down the theoretical value, right? Sorry, practical value, and theoretical value you have to calculate using the formula, right? Now this is all about resistive load. Now we'll move on to the next part, that is RL load. So RL load, how we'll do, that is RL load will be connected in this way. I'll just erase these wires. Yes, so this connections remains the same. Now for RL load, what we have to do is we have to, yes, for RL load, only thing what you have to do is you have to connect these two in series. That is, this resistance will be connected here, right? And this starting of the resistance will be connected to this point. Which point? This point. And then this end will be connected to this point, right? The only thing is here the resistance and inductance are in series, that's all, right? Now how to measure the voltage? We have to measure the voltage across R and L. So what I'll do, I'll connect this voltage across this point, and I'll connect one more wire from this point. Again from CRO the same thing. From CRO you'll have two wires. So one wire will be connected here and the other wire will be connected here, right, from the probe. So this will give you the readings for RL load. Now with the same connections, with the same connections, we have to connect the freewheeling diode. So the freewheeling diode will be connected in this way. That is only difference. The one wire you have to connect it from here to here, and again one more wire from here to here, right? So once you have done this, this experiment is nothing but it is RL load with freewheeling diode, right? Then you have to again vary the switching pulses with all the settings what I told earlier. You have to note down the waveforms and the V0 values, right? So for RL load, how is the connections? Here you will have resistance and inductance, and with freewheeling diode we'll have a diode here, right? So that is the experiment here, right? So here you have to note down the values, that is firing angle, whatever I showed you in the firing circuit. V0 practical is from the multimeter, and V0 theoretical you have to calculate using the formula for respective loads, right? I hope you understood this experiment. Thank you.